In logistic regression, let's focus on the binary case. We're going to directly estimate the conditional probability of y equal to 1 given x. Let's denote that probability by eta x. And of course, the probability of y equal to 0 given x will be 1 minus eta x. So eta x is a number between 0 and 1. And it would be difficult to model eta x by a linear model, for example, because linear model is unconstrained, but eta x is constrained between 0 and 1. So we're going to first take a logit transformation, meaning log the ratio or the odds. Basically, it's eta x divided by 1 minus eta x. So when eta x equal to a half, and that ratio inside log is 1, so we get 0. So the logit is 0. If eta x is bigger than a half, and that ratio inside the log is bigger than 1, and we get a positive number ranging from 0 to infinity. If eta x is less than a half, then the ratio inside log is going to be less than half, less than 1. So log of that number will be ranging from minus infinity to 0. And so now we're going to model this log and the ratio of eta over 1 minus eta by a linear model and x transpose beta. Here, for simplicity, we're going to absorb that intercept into the x. So our beta will be all the coefficients, including the intercept. Now, at every data point, we have the p-dimensional feature xi, the binary outcome yi, and the probability eta xi. So the unknown parameter beta is hidden in this eta function. So how should we estimate eta, or equivalently, how should we estimate beta? Following our usual path, next step, we have to design a loss function, and that will measure how happy we are with the observed y and the estimated eta x. And we could use L2 loss, y minus eta x squared. Apparently when y is equal to 1, of course we will want our probability to be close to 1, and when y is equal to 0, and we want our conditional probability eta x to be small. So it makes sense to use the L2 loss, but this loss function will be too flat to train, because y minus eta x will be a number less than 1, so you take squares, so it's even smaller than the original scale. And so when you want to take derivative, there are just not many gradients and large gradients there, so it's very easy to get stuck at some point, and it's difficult to get out. So instead, we're actually going to use the log likelihood as a loss function. First, the first equation where we know logit of eta is equal to x transpose beta. So next, let's express eta using beta. So eta x is going to equal to that ratio where we have the exponential exponential term appearing both in the numerator and the denominator. And the probability of y equal to 0 is 1 minus eta. Then we will have the ratio, but the numerator is 1. And next, we're going to write, merge the two expressions in that blue box as 1. So the probability of y equal to y, so here the lowercase y can take value either 1 or 0. So that we're just going to use a unified form. So it's sigma z. So if y is equal to 1, we take sigma z. So sigma z is basically the same as eta x. So sigma x transpose beta. So if y is equal to 1, we get sigma z. If y is equal to 0, we actually take 1 minus sigma z, which basically 1 minus eta x. So the sigma z is equal, take this form, e to the power z divided by 1 pi plus e to the power z, and z is just a shorthand notation for x transpose beta. So we can take log of this likelihood, and we get the sum of two terms. Depending on y is 1 or 0, we're just going to take one of the term. let me first explain what is sigma z. The sigma z is what's known as the sigmoid function. So it's S-shaped from -1 to 1, and z is any real number. Here, the formula in the red box basically a copy of what I had before. So we have our likelihood for one observation, explain some shorthand notations, and then log of that likelihood. So the log likelihood function over the n sample will be a sum of the last term. So we have yi times log sigma zi plus 1 minus yi times log 1 minus sigma zi. And what we're going to do next is just take derivative respect to beta, and set it to 0, set the gradient to 0, and then we're just going to solve it. You're going to find out it's different from the linear regression model. When we take derivative, set it to 0, and the solution is not in closed form. So we have to use some iterative algorithm to find the root of the derivative. So we're going to actually, along the way, we need to calculate the second derivative of the log likelihood function, which is going to be a matrix called known as a Hessian matrix. So next we're going to just compute the gradient, which is a vector, and also the Hessian matrix. And along the way, those expressions will help us to understand sort of the landscaping or the difficulty of this log likelihood function. When we take derivative respect to beta, we have to take derivative respect to this sigma z, the sigmoid function. So let's first do that calculation because we're going to use it. You can ignore the formula in the red bar because it's a copy of what we had before. Let's look at the formula in the blue box. So the derivative derivative of the sigmoid function respect to z. So here's a sigmoid function. First, we just do a transformation. We divided both the numerator and denominator by e to the power minus, divided by e to the power z. So we have, sort of this, the first equality is trivial. We just re-express this sigmoid function. And then now z only appear in the exponential component. So we take derivative by, first take square of the denominator, and then we take a derivative of this e to the power minus z. Along the process, we have two negative signs popped out. They cancel each other. So we get this expression. And then we break this ratio as a product of two terms. And then we times e to the power z on both numerator and denominator for the two terms. We have this. And then you're going to find out, well, because eta x is, this basically is 1 minus eta z, sigma z, times sigma z. So in summary, the derivative of the sigma function with respect to its argument z and is just equal to 1 minus sigma z and times sigma z. Okay. And again, you don't need to worry too much about the formula in the red box. It's just a copy of what we had before. Now we're going to take derivative respect to log of the probability. So we're going to take derivative respect to those two terms separately. Let's first look at the term, with a blue line. So we take derivative. Let's first take derivative respect to sigma z. So that will be y divided by sigma z. And then, so we just use chain rule, and then we take derivative of sigma z respect to z. That will be sigma z times 1 minus sigma z, as we just computed before. And the last step, we're going to take derivative of z respect to beta, which basically is x. You wouldn't get x transpose because this derivative should be a vector p by 1, p the same as the dimension of x. So we need x here. So all those expressions in front of x will be a number, and x is a vector. Now you can pause your this video, and then again use the chain rule to compute the derivative of the second term, and you're going to find out it is equal to this. Okay. Next, let's simplify those two terms. When we see something and we can cancel each other, like this one and this one, oh sorry, not this one going to stay, but this one and this one. Okay, so we get something like this. And we can further simplify some of the expression, because y times sigma z, here we have a minus sign in front of it. But for the second term, we have y times sigma z, but we have two negative signs, so it's a positive sign. So things can further get cancelled. You're going to find out those two. So eventually, the derivative respect to beta, the derivative of the log likelihood, is going to be y minus sigma z and parenthesis times x. Again, this is a number and this is a vector. So we are done with the calculation. I summarize what we just did in this blue box. The derivative of the log likelihood is equal to y minus sigma z, and that difference is a number, times x. And next, let's compute the second derivative, which is a derivative of this first derivative. We should get a matrix. And you're going to find out, well, beta only appear in sigma, so we can just basically ignore y. And the derivative of sigma z will give you sigma times 1 minus sigma times x. So you have another x here. You put them together, you're going to find out the second derivative is equal to minus x, it is a column vector, times sigma z times 1 minus sigma z, which is a number, and times x transpose, which is a row vector. So the product of the three terms is actually going to give you a matrix P by P. Okay, so let's put all those calculations together. And remember, our log likelihood is the sum of the log of the probability over all the observations. And let's first calculate first derivative. So that will be the sum of the derivative over this term inside the summation. And we did that calculation before, is yi times sigma zi times xi. So xi is a column vector. Suppose the blue bar is x1, okay, is a column vector. And this number in front of it, you can think about it as y1 minus p1. So what is a p1? And I apologize, I introduced a lot of redundant symbols. So sigma zi, by definition, is this, which basically is my eta xi, which basically is the probability of y equal to 1 conditioning you're at a location xi, so at ith observation. So I call this pi. So you're going to find out, and this basically is yi minus pi. So it is a number. And then you can look at the blue bar. So we have y2 minus p2, which is a number, the blue box, and times x2, which is a column, and all the way to and y3 minus p3, which is a red box, times x3, which is a column. And the sum of them should give you still a vector. You can rewrite in a matrix form. First, you stack all those numbers together. So that's y minus p is a column vector, because y is a p column, is a vector, and p will be this. You can stack all the probability p1 until pn as a vector. So it's y minus p, and then those color bars, every column is the p-dimensional feature for each observation. So the collection of those vertical column bars is actually X transpose, because in the original design matrix, all the features for every observation is actually row vectors. So we can put things together and we find out if in a matrix, using matrix form, the first derivative of the log likelihood function is equal to X transpose times y minus p. And now p is basically the probability we estimated using the current beta, and for each of the observations at each of the xi's. Now, what is the second derivative? And second derivative is minus sum of a column vector times a number. I'm going to call, so basically the pi times 1 minus pi. Let me call this a number, wi is just a number. and then times a row vector of xi. So you can think about this is x1, column x1 times a number, w1, times the row vector of x1 transpose. And this could be x2 column vector times w2 a number times x2 transpose a row vector, all the way, for x3. And you sum them together, the connection, if you use matrix form, is equal to x transpose times a diagonal matrix, where the diagonal entries of the w1 until wn, and times the original x. So in summary, if we use a matrix form, the second derivative of the log likelihood look like this. So let's summarize our calculation. The log likelihood function is given by sum of those expression, and the gradient is the expression is inside this sort of a purple box, and the second gradient is basically the Hessian matrix is in this blue box. And you're going to find out the Hessian matrix is negative semi-definite, meaning minus the Hessian matrix, which is x transpose wx, is semi-positive definite. It means that if I times a vector alpha transpose times alpha, and this is going to give you a number, you can show this is always bigger or equal to 0. Well, this is because W is a diagonal matrix. Sort of you can rewrite this, you can break W as W a half, and W a half is symmetric, and you can merge this as one vector, the remaining another vector, and so the whole thing can be written as a norm square, so it's always non-negative. So the Hessian is you can think about this Hessian matrix always negative, less or equal to 0. And for one-dimensional function, what if its second derivative is always negative, like this, or like this? So it's a concave function, meaning any local minimal is going to be global. Local maximal is going to be global maximal. If you are not familiar with concave, you can think about minus log likelihood is going to be a convex function. So this wouldn't be a convex function. Convex function should look like this or this. So it's easier to find, and it's easier to find its global optimal point. You just follow the gradient. So for logistic regression, we can find its MLE by iteratively using the Newton-Raphson algorithm to find the root of the derivative. How we use Newton-Raphson to find the root of a function? You start with some value x0, and then for the one-dimensional case, and you draw a tangent line at x0, you hit at x1, and then at x1 you draw another tangent line, you hit at x2. You can see you're already very close to the real root, which is a red point. So let's summarize what we are doing here is the Newton-Raphson means if you're at the current location x0, you do a first-order Taylor expansion to approximate the function fx. So your first-order Taylor expansion is fx0 plus its derivative and times the linear term. So you're gonna set this one to be 0, and you can solve what is x, the root for this linear function. And it turns out to be the old value, which is the x0, minus something is f divided by f derivative, and they're all evaluated at x0. Now, in order to use Newton-Raphson, remember we want to find the root of the first derivative of the log likelihood function. So we're going to replace our f by, if we use this formula, we're just going to start with beta 0, and then we're going to replace the f by the first derivative, which is x transpose y minus p, we just computed before, and divided by the second derivative, which in the matrix form, so it's the inverse. We're going to invert this matrix, and there's some kind of a you get two negative signs, you get a plus now. So this is the updating formula. If you're at the current value beta 0, you can update your beta by this summation. So you get your new beta 0 and you keep doing this. Now, sometimes we can rewrite this summation by this. We're going to absorbing the beta 0 inside the parentheses. So you can see the expression in front of beta 1, all of them, is basically a matrix inverse times the matrix itself. So they cancel each other. And for the original y minus p, because you have a w outside, so you can have a w inverse inside. And what's interesting about this expression is you can think about as if you already have current value beta 0, and then you can just x times beta 0, which is the current fitted value, plus sort of weighted residuals, because y is what you observed, and p the probability you estimated. So you look at the difference, you do some weighting, and the sum, the blue expression basically is a vector. You call that your sort of pseudo response vector z, and then you basically solve a weighted regression model, because your new beta is going to be x transpose w, x transpose inverse, x transpose wz. So this is the this is the least square coefficient when you are running a weighted least square, because if there's no w, that's ordinary least square. But w, which is a diagonal matrix, you basically assign some weights for each of the n observations. So to summarize, here's how we compute the MLE for logistic regression. So logistic regression, the log likelihood function is a nice concave function. So any local maximum will be a global maximum. We don't need to worry about getting stuck at a local optimal point. And the MLE is obtained by the following weighted least square. We start with some initial value beta 0. We compute this pi, which is the probability we estimated using the current beta 0 for every xi. And we form our diagonal matrix, where the diagonal entries are pi 1 minus pi. And we get our sort of a pseudo response z. And then we just run a weighted least square to get our new beta. And then we can loop. And then we're going to, once we get our new beta, we can re-update our P and W matrix and just iterative through this step until convergence. So this is how we compute the MLE for logistic regression, and you can, of course, R will handle all this. Before closing today's lecture, I want to explain a small glitch with logistic regression when the data are well separated. What I mean by data are well separated, let's look at this example where the red points are from class 1 and blue points are from class 0, and data are two-dimensional. So we have our features are two-dimensional. Right now, if we want to use a logistic regression, let's ignore the intercept. So we require intercept is 0. And then we want to find out the two regression coefficients, beta 1 and beta 2. Let's look at the log likelihood. And for the likelihood calculation, for red points, what's entered in the calculation is eta x, which is the expression in red box. That's for the red points. But for blue points, what's entered in the log likelihood will be 1 minus eta x, which is expression in the blue box. So what's difference is for the red box, there is a minus sign in front of the exponential component, but you don't have that in the blue box. And so we have 4 data points. Let's first try coefficient beta 1 equal to 1, beta 2 equal to 1. Let's look at the what's the likelihood for the 2 red points. Because they're all in the first quadrant, beta 1, beta 2 are 1. So what's in the exponential component will be x1 plus x2. Because x1, x2 for the red points, they are both positive. So so this number will be e to the power some negative number, so it's less than 1. So this ratio will be bigger than half, which is good. And similarly, you can do the calculation, look at the calculation for the data for the 2 blue points. Because they're in the 3rd quadrant, so both x1 and x2 are negative. Again, we're going to get a probability which is bigger than half for the 2 blue points. So far so good. Now let's try if we're going to increase the beta 1, beta 2 to 10, so make them larger. And you can do the calculation again, and then you're going to find out for both red and the blue, this term is getting smaller, much smaller than 1. So the whole ratio is much bigger than half. So that's good. So that means we think 10 is better than 1. Next, let's try B1. The first and second coefficients are equal to 500. Again, you can think about what's the likelihood for the red points and what are the likelihoods for the blue points. Now this term, the component in the exponential component is is very, very negative. So the whole number is the e to the power that number is going to be very small. So again, everything's moving to the right direction. The likelihoods are even better than before, is getting closer to 1. So you quickly realize there's a problem because the likelihood for both the red points and blue points, because they are well separated, then there's a way you can just keep increasing the coefficients, and the likelihoods are moving to the ideal, the desired direction. And so if we really want to maximize the likelihood, eventually we can push those likelihood in the red box and blue box to be close to 1 by setting those beta 1, beta 2 to be very, very large, of huge magnitude. So if you run this data in R, you're going to get an error, a warning message telling you the algorithm does not converge because the coefficients keep getting larger and larger and there's no ending. So that's sort of a known problem with logistic regression when data are well separated. Because that's when data are well separated, there is a way you can make the likelihood approaching to the boundary point, either 1 or 0, going to 1. So the magnitude of the coefficient is too large and the algorithm won't converge. However, this is why R will give you a warning message instead of an error, because you can still use the model to do prediction, because this separating line, this line is actually well defined, because no matter your beta 1, beta 2 equal to 1, 10, or 500, they all refer to the same line, which is x1 plus x2 equal to 0. So the boundary and decision boundary is well defined. Of course, here you could have multiple decision boundary, but at least for this regression model, although my coefficients are going to 0, but the line such that the predicted probability is equal to half, that line is well defined, because on one side of the equation is 0, so it doesn't matter. You times 500 on both sides, and although you change the coefficients, but the line stay the same.